The final video for chapter 13 is going to be on angular momentum and the conservation of angular momentum, and this is covered in chapters 13.6 and 13.7 of the textbook. Okay, so a quick reminder, if you remember back in chapter 10 or 11, whatever it was, we defined linear momentum, which was a vector, and it was the mass of an object times the velocity of an object. Now, we can also define something called angular momentum for a particle, and for a particle we're going to use L to stand for angular momentum. It is a vector, just like linear momentum is, and it's R cross product with the linear momentum P, where R here is going to be a position vector. Typically you do it from the axis of rotation to the location of where the particle is, although in principle you can calculate the angular momentum relative to any point. So just remember, so this is position, linear momentum, and we're going to use the cross product for this. Now, for an extended object, well, again, you do what you usually think of. You imagine slicing it up into a million little bits. For each one of those little bits, you treat it as a particle. You add the linear momentum for each of those, or the angular momentum for each of those little particles together, and it becomes an integral. You do the integral, and you wind up that the angular momentum for an extended object is the moment of inertia I times the angular velocity omega. Now units, well, it's a distance times a momentum, so SI units are going to be kilogram meters squared per second. And also you should remember linear momentum, angular momentum, just like linear momentum, is a vector. It has a direction, and the direction is the same direction as the angular velocity omega. And if you remember how we defined this, we used the right hand rule. So if you have an object that's spinning, so you take your right hand, you curl your fingers in the direction of the rotation, and omega is given by your thumb. So omega is always directed along the axis of rotation, and it's given by the right hand rule. So now that we have angular momentum, we can write yet another version of Newton's second law, the rotational version, and we can do this in terms of angular momentum. And hopefully there shouldn't be any surprises here. So if you take the sum of all the external torques on a system, that's going to equal the time derivative of the total angular momentum of the system. So this should hopefully look quite similar to what we had for linear motion, right? We had the sum of all the external forces was dp dt. In the rotational version, we replace force with torque and linear momentum with angular momentum. Now, of course, the interesting part comes in if your net external torque is zero. So if your net external torque is zero, well, then this time derivative, dl dt, is zero. And if the time derivative is zero, that tells you that this total angular momentum, is constant. So this is the condition for conservation of angular momentum. If the net torque on an object is zero, or the net external torque on a system of objects is zero, the angular momentum is going to be conserved. It'll stay the same.